know it doesn't. All right, permutations, where all objects are distinguishable, which means we can do what? Tell them apart, right? So they're distinguished, we can tell them apart. Because guess what tomorrow is? Permutation, where some of the objects are the same, right? You can't tell them apart. But here we can. There are 5 different characters in the school play. 8 students are available to play any of the characters. How many different rosters of actors are there? So really, this is just a fundamental counting principle question, right? We have 5 things. These things being actors, but we have 5 of them. And how many choices do we have for the first part? 8. And then, notice when I say and, right, it's multiply. And then, and 1, 2, 3, 6. That's 5, right? 1, 2, 3, 4, 5. And that is, now what do we got? 21, 28, 40, 64, 100, 69, 20 or something? I don't know. Work it out. You got a calculator. What do we get? Thank you. Ms. Smith will be happy. I will pass that on to her.
6,720.
That was close. 6,720. So there are 6,720 ways to cast this play if we have 8 people to choose from and we need 5. Ms. McCade has 5 different chocolate bars to eat, Halloween-sized ones. How many different orders can she eat any 4 of them? All right, well, so same deal, right? Fundamental counting principle. We have 4 chocolate bars we are going to eat. How many choices do we have for the first one? We've got 5 choices, right? So we have 5 chocolate bars. For some reason, she's only going to eat 4 of them. And for the second one, and for the third one, and for the fourth one. So that's 120 different ways. 120 different ways in which you can eat 4 chocolate bars out of a set of 5. So permutation notation, right? So we know that a permutation, the definition of a permutation is a distinguishable arrangement of objects. And yesterday when we did permutations, we just arranged all of them, right? So we would say it's n factorial. You got 5 things, it's 5 factorial. You got 4 things, it's 4 factorial. Well, what if we're not going to choose all of them? So we have this formula, NPR, which is equal to n factorial over n minus r factorial, where n is the total number of objects, and r is how many of them you are arranging. Okay, now, there's a note here, which is 0 factorial, right? Like, what if n is equal to r? What if you're arranging all of them? What's the formula? Well, you're going to get npn, right? Because you're going to arrange all of them, which will be n factorial over n minus n, which is 0 factorial. But we know if we're arranging all the objects, like 7 objects, it's just 7 factorial. So npn is just equal to n factorial. And what that means is that because we're going to get a 0 factorial here, we're going to define it as 1 so that it won't change that value, right? So the value does come out being n factorial. All right, let's do some problems. Using the letters in the word English. So imagine those are on Scrabble tiles. You got the little Scrabble rail sitting in front of you. These are the letters. State the number of 3-letter arrangements. Okay, so first thing, how many letters are there? Okay, so we got 7 letters, right? So how many 3-letter arrangements? Well, NPR, we would say, is 7P3. So I have a set of 7 objects. P, we want all the permutations, right, which is distinguishable arrangements of any 3 of them. Using the formula, that would be 7 factorial over 7 minus 3. Let's clean that up. 7 minus 3, NPR. N is 7, R is 3. So n factorial, 7 factorial over 7 minus 3, right? N minus R factorial, which will be 7 factorial over 4 factorial. And we said, hey, we know what to do with that yesterday, right? I can expand the 7 factorial, get 7 times 6 times 5 times 4, and say, let's stop there, because on the bottom we have 4 factorial. So it's going to be 7 times 6 times 5, which is 210. And that's the one time we're going to work it out the long, painful way. There's a way. You got a calculator. We can use a calculator. Let's see where it is and how we use the calculator to do that. Okay, so we want to run a permutation. We want 7. So we start with the 7. We go into the math menu. We're into the math menu. We want to get over to probability. I like to go left. It's only 2. NPR is actually built in, number 2. So we go 7, we hit the NPR key, and if you have the newer calculator, this is what it looks like. You see the 7, subscripted, you got a big P, and then we're going to put in the R, which is 4. What do we want? 3-letter arrangement. So 7P3, hit enter, 210. Okay, so I think it's good. You see it done once. Once it's expanded out. After that, it's like, hey, calculator does it. If you have the older calculator, you're going to see 7, then NPR, and then 3, and that's fine. Then you hit enter, and you get 210. All right, what if it's a 4-letter arrangement? 4-letter arrangement is going to be 7P4. All right, so we got a couple of choices. I can just go second enter, right? Bring that back down, and then just say, hey, let's change it to 3 to a 4, and then hit enter. Right, and get 840. Okay, so 4-letter arrangement, there'll be 840 different 4-letter arrangements. Remember, distinguishable, different, right? Order matters. It's another way of saying it. Right? So you're going to see that all the time. The order matters. Distinguishable, I can tell them apart. Different. 5-letter arrangements. Give that one a shot, come up with the answer. So show what you're doing. You're going to do 7P5, right? That's equal to, and I'll redo it. So math over couple, number 2, 5, 7P5, 2520. If it was 7-letter arrangements, that would just be 7 factorial, right? There's no point doing 7P7. Just go 7 factorial if it's all of them. All right, here we go. First use of the word or in this context. The number of 3 or 4 or 5-letter arrangements. Now, likely, we wouldn't even say that. We wouldn't say 3 or 4 or 5, right? You just say a number of 3, 4, 5. Maybe you would say that. But you should say that. You should be very explicit about it. So 3-letter arrangement. Okay, so that's done 7P3, right? That's the number of 3-letter arrangements. Or, what do we do with or? We add 4-letter arrangement, 7P4. Or plus 7P5. Now, we got those all nicely worked out for us. So we go equals. If we didn't have them worked out, we'd now be working each one out individually. So we say 210 plus 840 plus 2520 equals, what is it? 3,570? Okay. I knew it ended in 70 because I added up the 20, the 40, and the 10. I haven't got to the other ones yet. 13, 15, yeah, 5 makes sense. Okay. So with or, right, with and, you're multiplying. And so, again, if you did this with fundamental counting principle, three-letter arrangements, you would say, I have 7 choices for the first, and then 6, and then 5 is 210. Okay. Or, and then we add, and you could do this whole question with fundamental counting principle, right? You could go blank times blank times blank for the 3, 7p3, the arrangements of 3 letters, plus, and then blank, 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 right? Blank times blank times blank 4 times. 4 boys and 2 girls are to be arranged in a row in the classroom. How many arrangements of the 6 students are there? All right, so when we do anything with permutation or combinations, the next part of this unit, we have to ask ourselves, are there any restrictions here? Right, I got 4 boys and 2 girls. Is there any restrictions? It says range of 6 students. No. Right, doesn't say that it has to have a girl in the front, girl in the back, or anything like that. So how many ways, how many arrangements of all 6 of them are there? Just going to go 6 factorial, right? Or you could go 6p6, which is equal to 6 factorial, which is 720. And obviously we don't want to do a tree diagram and list them all, right? It's not like there's 9 different outfits we have for playing a sport or something like that. It's like there's 720 arrangements, right? I just want to know how many there are. I don't really care about what each of them is. If the first and last person in the row must be a girl, how many arrangements are there? So at this point, I like the fundamental counting principle, right? I'm just going to go back to the fundamental counting principle. All right, I got 6 students to arrange. 1, 2, 3, 4, 5, 6. That's a girl. That's a girl. How many girls do I have to choose from to be the first students? Go back up to 4. 2, right? 2. All right, we got to deal with the restrictions. So how many girls do I have to choose from to go at the end? There's only 1 left, right? How many boys do I have to choose from to go here? And then. So that's going to give us 48 different arrangements. Yeah, another way you could say this is, I have 2 times 4 factorial. Or actually, you know what? Actually, you'd say 2 factorial. I have 2 factorial ways, because 2 factorial is 2. So you sort of got to be careful when you're just saying 2. Do I really mean just 2, or do I mean 2 factorial? So I have the ways I can arrange the 2 girls, which is 2 factorial ways, which is just 2. And then the 4 boys could be arranged in 4 factorial ways. And that gives me 2 times 24, which is 48 ways. So I prefer a fundamental counting principle for that, because I get to say, all right, this many, and then this. What if the 2 girls must sit one in front of the other in the front of the row? How many arrangements of the 6 students are there? So it really doesn't matter. As long if you're specifying where the girls are, there's always going to be 48 arrangements, right? Because you're specifying where they are. Oh, 1 on each end. Okay, 2 and 1. Both in the front, 2 then 1. Right? And then the boys, well, 4, 3, 2, 1. The boys are always 4, 3, 2, 1. It doesn't matter where they are. Whether they're at the end of the row, at the beginning of the row, or in part B, they're in the middle. It's all 48 different arrangements. Out of the 720, right? Remember, there's 720 total. 48 of them have the girls on either end. 48 of them have the girls in the first and second place. and so on. Student Activity Council sold 200 tickets in a raffle. How many ways can the tickets be drawn to award the first, second, and third prizes if each winning ticket drawn is not put back prior to the next draw? Okay, so we call that without replacement, right? If we do replace it, they're different numbers. Two different ways, right? You can use fundamental counting principle. So first place here, how many choices do I have for first place? Second place? Third place? Okay, so work that out. You can also say, I have 200 tickets. How many arrangements of 3 of them are there? Right? How many different ways are there to arrange 3? So here, 200 times 199 times 198, 7,880,400. And 200 math or probability 2, 3, 7,880,400. Okay, so fundamental counting principle works, permutations works, just getting a number. So if they're just giving you the answers as numbers, really doesn't matter which way you do it, but they may show you the answer as 200 times 199 times 198. They may show the answer as 200p3. Okay, so you just have to recognize that there are different ways, but they're saying the same thing. Student numbers at a college are 7 digits in length and cannot start with 0. If digits can be repeated, how many different student numbers are there? Okay, the only way to do this is with fundamental counting principle, right? If you're repeating the digits, okay, because then we're not saying you can only choose each one once, right? That's a permutation. They're all distinguishable. If I can repeat. All right, so we got 7 digits. 2, 3, 4, 5, 6, 7. So if the first digit can't be 0, how many digits do we have to choose from? This one is 0. Right? So we have 9. Okay, I can repeat digits. How many choices for the second digit? 10. Right? Because now 0 is back in. Right? You have 0. How many choices for the third digit? 4th digit. And then, which gives us 9 followed by 6 zeros. 9 million. Oh, that sounded like a phone. I know it sounds like drop line earlier. Can we look? Oh, is it okay? If digits cannot be repeated, how many different student numbers are there? Okay, not equal to, clean that up. Not equal to 0, 7 digits. Yeah, me personally, I like fundamental counting principle. Right. Kind of my go-to method, fundamental counting principle. All right, can't be 0. How many digits for the first digit? 9, right? Same as before. Right? We got 10, this can't be 0, so we have 9 to choose from. How many choices for the second digit? 9. All right, so the 0, right, that's gone for the first digit. Let's say we choose that one. Then 0 comes back in. Doesn't stretch well. Okay, so the 0 was out for the first digit. We had 9. We pick one of the others. Now we have 8 left, but the 0 comes back in. So we have 9, and then, and then, and then, and then, and we're just going to plug that into our calculator. $544,320. which is substantially fewer arrangements, right, than if you can repeat the digits. Assuming that's right. Maybe it's wrong. I don't know. What? Okay. You're both wrong. No. Or you're both right. I'm going to go with likely you're both right. We crowdsource answers in this class, right? Like especially when we do like a regression or something, because if you mess up, you got a different thing. But if like 5 people have the same thing, we didn't all mess up the same. Very important when you're doing regressions on tests, diploma, whatever. Check over the numbers before you run the regression. Okay, double check your entries. Because if you get it wrong, it's just wrong. And if it's a numeric response question, it's just wrong. If it's written response, it's just wrong. If it's multiple choice, you're going to know it's wrong because you won't have the answer there, right? Likely. First digit is a 1. It means the student will start college in 2021. How many student numbers are available for students starting in 2021 if digits cannot be repeated? Okay, give it a shot. You have all the tools you need. 2 examples. Well, one example that's on point. And often they do it that way. Like your student number, your CBE student ID is actually based off of the year that you were first registered in the CBE, et cetera, et cetera. There's stuff we can tell about you based on your CBE ID, which doesn't get used much these days.
It gets confusing when there's someone with the exact same name as you born on the exact same day.
Well, what happens is the last 2 digits of your CBE student ID are which one of you registered first. So 01 is the first one to register, 02 is the next. But it's not the same name, it's the same birthday, because your birthday is in there. So if you're like 05, that means 4 people registered before you that had the other information being the same. Must be 1. So how's that look? So the first digit's got to be a 1. Again? Man, hang on a bit. First digit's got to be a 1. You can't repeat the digits. So there's one choice for the first digit, right? Then 9, then 8, then 7, then 6, then 5, then 4, which is what? 1/9 of that. So I could divide that by 9, or you could just tell me.
60,480.
60,480. So unless it's a really big college, they're not going to run out of student numbers for the people registering in 2021, right? And most places are not going to have an enrollment of 60,000 students. If the last digit is a 0 and digits cannot be repeated, how many different student numbers are there? Right? Do it. Now, some of this we can probably do with permutations, but at some point it's kind of like, why bother? It's easier just because. But it's the same. Then we should have like E. What if both C and D? First digit's got to be a 1. Well, we could do that, right? You deal with all of your restrictions. You put down your blanks. I got 7 blanks, student number. You deal with your restrictions. It's got to start with a 1. It can't start with a 0. The nice thing here, if it does start with a 1, you don't have to worry about starting with a 0. It's starting with a 1. What do they do for 2020 then? Why doesn't it start with a 0? Don't ask that question. You haven't figured it out. Car dealership has 9 different vehicles they would like to line up in the car lot. how many different arrangements are possible? It's like the easiest question. How many? So your chance to say 9. Or 9 factorial. Any restrictions? Nope. Got 9 things, right? 9 different vehicles, right? That's important. No repetition, right? I mean, if there's 2 red Corvettes or something, and we can't tell apart, they're exactly the same as far as their options or whatever. That makes it different. All right, gonna get it right to this time. All right. One of these days, I learned 9 factorial eventually. So 362,880. If there were 10 of them, you just throw another 0 on there. You're gonna multiply that by 10. But there aren't. Get rid of that. How many different arrangements are possible if the Jeep Wrangler is in the middle of the lineup? Now, you could do 9 blanks, right? Right. And you're going to put the Jeep first in the middle. You're going to put a 1 in the middle. And then you're going to go 8, 7, 6, 5, 4, 3, 2, 1. So you just say, look, I placed the Jeep, and then I have 8 other vehicles to arrange. So they can be arranged in 8 factorial ways, right? So the Jeep, take it out of the group of 9, stick it in the middle, and then say, you got 8 spots left, I got 8 vehicles, that's 8 factorial, which is what? 40,000 something? 320. How many different arrangements are possible if a GM truck is at one end and a Chevy truck is at the other? GM at one end and a Chevy at the other. Yes? No? Yes? Good. How'd you do it? So it is 2 times 7 factorial. I sort of prefer it as 2 factorial because really we're arranging the GM and the Chevy, right? So there's 2 ways that we could do that, which is 2 factorial. I know it's also 2, but. And then we've got the other 7 vehicles. That's one way. You can do fundamental counting principle, right? Throw down 9 blanks. Okay, so I've got the GM or the Chevy, G or C, and then whatever's left, C or G, the other one, the remaining. So 2 choices for the first, it's either the GM or the Chev, and then 1 choice for the second, it's the other one. And now I have 7 vehicles left to place, but they could be done in 7 factorial ways. So 2 factorial, the arrangements of the GM and the Chevy, times 7 factorial. How many different arrangements of the letters of the word oranges? How many letters are there in oranges? 7, right? 7. Are they all different? Yep. Okay. So they have to be different, right? Like today they're all different. Tomorrow they may not all be different. No restrictions. How many ways can you arrange 7 objects with no restrictions? 7 factorial, right? Which is? So 7 factorial or 7p7. Or 7 blanks. All the above, right? So if they've worked something out to a number, it really doesn't matter which way you do this, right? 7 factorial, 7p7, 7 times 6 times 5 times 4 times 3. Well, imagine you get 50, 40, you find that as an answer, you're happy, and we're done here. If they give it as 7 times 6 times 5 times 4 times 3 times 2 times 1, just like, oh, yeah, I thought it was 7 factorial. They wrote it out expanded. Great. So you're going to see a lot of them where they do a fundamental counting principle where it is expanded, right? And it's like 3 different letters followed by 4 digits, like the car license plate or something. First letter must be N. How many arrangements are there? The first letter is N. Yeah, so the way I look at it is this. First letter is N, then I have O-R-A-G-E-S, right? That's what's left. How many letters are left? How many ways can these letters be arranged? Okay. So just think of it as, I got my little Scrabble tile thing, right? Got O-R-A-N-G-E-S. I'm going to take the N, I'm going to stick it down there. Okay, now what's left? Well, I have 6 letters, they go in. I have to use them all in this case, because we're arranging all the letters. There's different arrangements of the letters. We're not choosing 3 letters from this. The vowels, O, A, and E, must be together in that order. Okay, so here's how I think about this one. I'm going to combine OAE onto one tile and I'm going to glue them in place. So now how many tiles do I have to arrange? So I've got the OAE is 1, and then I've got the R, the N, the G, and the S. So I have 5 things to arrange. How many ways can we arrange 5 things? 5 factorial, or 120 ways. Right. So that's what the OAE, but they have to be in that order, right? So they're glued together. There's the glue. The vowels, A, E, and O, can be together, but in any order. So I'm going to make a super tile that has OAE on it. So we're going to look at this and say, how many tiles do I have to arrange? Okay, well, including this super tile, I've got 1, 2, 3, 4, 5. That can be done in 5 factorial ways. But on this tile, how many ways can I arrange these guys? 3 factorial ways, right? So we're going to go with 3 factorial times 5 factorial.
Wait, why did R and D S? Why is that 4?
Well, it includes OAE. That's also a tile. So I have a tile that has the 3 letters on it, and I have 4 other tiles.
So wouldn't it be like if the circle wouldn't it be like 1 times 1, and then times 4 times 3 times 2 times 1?
Well, these ones are glued together, right? So are you okay with there being 5 of them here? Like 5 tiles? Okay, this one here, O, A, and E are together, but they've got to stay in that order.
Yeah.
Okay, so that's one object. There's 2, there's 3, there's 4, there's 5.
No, I didn't know they counted those.
Well, they count as an object because they're still, right? Like one of the objects could be OAE, RNGS. We could have OAE, NRGS. That's another arrangement. OAE, we can have R and then the OAE and then the NGS.
Yeah.
We can have RN, then the OAE. Okay. Does it make sense that we're arranging 5 objects?
Yeah, now it does.
Okay.
I thought like it would count as 1 factorial.
Well, we're not arranging this,
Yeah.
right? Because they have, but these we are arranging.
Yeah, no.
Okay, so we got 5 tiles, right? That's 5 factorial ways. For every one of those arrangements, these guys could be OAE, AEO, EOA, etc., etc. Right? There's 6 arrangements. So we're going to take 5 factorial, that's the ways to arrange the tiles, and then for the tile with the vowels on it, which I really should have written as AEO, but whatever, for the tile with the vowels on it, those can be arranged 3 factorial ways. So 3 factorial times 5 factorial. gives you 720 arrangements. And